In this video, I'm going to show you three marked ruler constructions. One has been known since the times of Archimedes. One was known in ancient times, though I think the version that I'm going to present is a slight generalization of it. And one may or may not have been known in ancient times, but the earliest source I can find for it dates from 1975. So here are three constructions that can be done with a compass and an unmarked straight edge, the sort of compass constructions that are described in Euclid's Elements, but they all have the property that you can't run them backwards. First one, if you give me an angle theta, I can certainly triple that angle. I can construct an angle of 3 theta. On the other hand, if you give me an angle and ask me to trisect it, I'll say, I can't do it. I can trisect a line segment, okay, but I can't trisect an angle. If you give me a regular heptagon, I can, with considerable difficulty, split off a segment of length 1 and leave behind a segment whose length I'll call y, where y, which is really the ratio of two line segments, satisfies the cubic equation y cubed plus y squared minus 2y minus y1 equals 0. And you've already seen that this value of y is equal to twice the cosine of 2 pi over 7 radians. In other words, this y is intimately related to the angle that you need to make a regular heptagon. On the other hand, we don't yet have a way of dividing up a given segment into segments of length y and length 1 for which this equation is satisfied. If you give me a segment of length y and a segment of length 1, I can construct a new segment whose length is equal to y cubed over 4. On the other hand, I don't know how, given the segment of length z, I can reverse this to construct a segment whose length is the cube root of 4z. And now what I'm going to show you is that in each case, I can solve the reverse problem if you allow me to put two marks a unit distance apart on my straight edge. So let's start with the first of these and consider how we would triple a given angle. Here's the angle between two lines at O. And here's what I do. I set my compass to have radius 1. I draw a unit circle at O, and it intersects this arm of the angle that specifies point A. Then I draw another circle of radius 1, see where it intersects the horizontal line from O, the other arm of the angle, and that locates point B for me. If I look at the triangle OBA, I see it's isosceles because it has two sides of length 1. It has two equal angles theta, and the external angle at vertex A is, according to Euclid, the sum of these two angles, or 2 theta. Now I extend the line BA until it hits my first circle at C, and I look at the triangle OBC. Clearly, this angle is an external angle of that triangle, and according to Euclid, it is the sum of these two angles, theta and 2 theta, and therefore the angle at O is 3 theta. So the question is, how do we run this backwards? Now, in this diagram, everything that's already drawn is going to be shown in red. The other lines are lines from my original diagram that I haven't yet reconstructed. So I'm now going to start with an angle that I will call 3 theta, and my goal is to construct an angle theta. And I'm going to start by drawing a unit circle at O. So I now have this circular arc, and I'm going to extend the line at O a long way to the left. So I've got point C from the intersection of the circle and one arm of my original angle. Now I take my marked ruler. There are 2 points on it, unit distance apart, and I place the marked ruler so that one of the marks is at B, the second of the marks is at A, and the ruler passes through point C. There's no way to do this except trial and error. That is, you can't do it by sliding along a certain line or rotating about a certain point. You've just got to keep fiddling with the ruler until miraculously one mark coincides with A, another mark coincides with B, and the point C is on my circle. But once I've succeeded in doing that, I've replicated my original diagram, and we've already proved that this angle is 3 times that angle. So if this angle is 3 theta, that angle must be theta. This construction, as I've mentioned, was already known to Archimedes. Now let's tackle the heptagon problem. I've discussed this in some detail in a previous video. What we want to do is say that for the angle theta that we want between 2 vertices, the cosine of 4 theta and the cosine of 3 theta are equal, so their difference is 0. I use a trig identity to substitute for cosine 3 theta. I use another trig identity to substitute for cosine 4 theta. I combine these to get a quartic equation. I pull out the factor cosine theta minus 1, and I have a cubic equation for cosine theta. And to make this look a little bit simpler, I call 2 cosine theta y, whereupon this equation becomes y cubed plus y squared minus 2y minus 1 equals 0. Sorry, plus 1 equals 0. My mistake. I can't change that minus sign to a plus sign. Okay. So again, I'm going to solve the reverse problem. Given the heptagon, I'm going to construct a line segment split into 2 pieces such that the length y of one of those pieces satisfies the cubic equation I just showed you. And here's how I'm going to do this. The heptagon is inscribed in a circle whose radius is the square root of 2. The length 1 is somewhat less than the square root of 2, and I will draw a segment of length 1 going horizontally from the center of the circle. And I will extend that to a square. Since the side of this square is 1, the diagonal CE has length square root of 2, and the point E is also on the circle. Now I'm going to construct an isosceles triangle in which each of the base angles is 3 times the remaining angle. Remember, Euclid's secret for constructing a pentagon was each base angle was twice the remaining angle. How am I going to do this? Well, here's a vertex of the heptagon. Here's a vertex of the heptagon. The angle between those two is equal to 4 times beta, where beta is pi over 7. And since I have supplementary angles at C, the other angle is 3 times beta, where beta equals pi over 7. So this angle is 3 pi over 7. And having extended it so it meets this perpendicular bisector, I construct the line joining B to where that line met the bisector. I now have an isosceles triangle, so both these angles are 3 beta, and what's left over at the apex is the angle beta, which is pi over 7. Now let me extend this construction a little bit further. I will consider the point P where the line AB meets the circle, and I will call the distance from P to B y, while the distance from P to A is going to be equal to 1. This distance is equal to the side of the square. Okay, now I have to prove that y satisfies the cubic equation for the heptagon. I'm going to do this using the law of cosines. Here I have a triangle. This side, BC, has length 1. This side has length y. This is not a right angle, so I can't just use the Pythagorean theorem, but I can say that if I apply the law of cosines at vertex B, I find 1 squared plus y squared minus twice 1 times y times cosine 3 beta equals the length PC, and since that's the radius of the circle, its square is equal to 2. If I subtract 1 from both sides, I get y squared minus 2y cos 3 beta equals 1. Let me multiply this through by y plus 1. So y plus 1 times y squared minus 2y times y plus 1 times cosine 3 beta equals y plus 1. But now look at this isosceles triangle. I take y plus 1, I multiply by the cosine of 3 beta, and I get half the length of BC, and therefore it follows that if I take twice y plus 1 times cos 3 beta, I get the full distance from B to C, which is equal to 1, and that happens to be what's in the second term of my equation here, except for y. So I conclude that y plus 1 times y squared, which is y cubed plus y squared, minus what's left over from here, just y, equals y plus 1, or moving everything onto the left, y cubed plus y squared minus 2y minus 1 equals 0. Now the challenge is to reverse this construction. So again, I'll follow the same convention. Everything that's in red has been drawn. Things that are still in black have not yet been drawn. So I'm now going to start with my segment BC, whose length I call 1. I'm going to construct a square of side 1. The diagonal of that square is the square root of 2. So if I draw a circle centered at point C that passes through the opposite corner of the square at E, I have a circle whose radius is the square root of 2. I can also easily construct the perpendicular bisector of side BC. I don't know where point A is yet. I don't know where point P is yet. And that's where my marked ruler is going to serve me well. Here's what I do with it. I place the marked ruler so that it passes through point B. It cuts through the circle and it intersects the perpendicular bisector, and I place the marks so that one mark is at A on the perpendicular bisector, the other one is at P on the circle. And now I maintain I can find all the vertices of the heptagon. What do I do? Well, first, I complete the isosceles triangle. Previously, I had the side from B to A. I now draw the side going from A down to C to complete the isosceles triangle. That's going to intersect the circle somewhere, and I will call that vertex 1. I will extend BC to the right until it hits the circle. That gives me vertex 3, and now I'm home free because I've got two vertices of the heptagon separated by one other vertex. To find the separating vertex, I just take this angle at C, which is equal to 4 beta, and bisect it to get an angle of 2 beta here, an angle of 2 beta there. And then, now that I know vertex 2, I can construct a circle whose radius is equal to the distance from 1 to 3, and that will cut the circle at 7 and 4. I do the same thing starting with point 3. I've got vertex 5. I do it again starting with vertex 1. I've got vertex 6. Join things up, and I have the entire heptagon constructed. Finally, I want to show you how to construct cube roots using a marked ruler. And the construction I'm going to reverse is a rather strange construction that allows me to take a line segment whose length is in between 1 and 2 and construct its cube. So here is length 1. Here is length y, which is greater than 1. And I will call the point on the horizontal line whose distance from B is the value y, e. Now I'll draw a circle of radius 1 centered on B. I can construct a segment whose length is equal to y squared over 2 by standard Euclidean techniques. So I will assume I have already set my compass so that it will draw a circle of radius 1 plus y squared over 2. I draw that circle centered on E, and that intersects my original unit circle at A. I unfortunately do this diagram in such a way that C lies on the circle, but that's not essential to the construction. And in general, for arbitrary values of y between 1 and 2, it won't be the case. So now I've got point A as the intersection of the two circles. I drop a perpendicular, and I double the distance from the perpendicular to B to get a point C such that the distance between B and C is equal to Z. Well, we can use the Pythagorean theorem to see what we've accomplished. Here's the perpendicular I dropped from A. I'll call its length h, but my major algebraic goal will be to get h to disappear. Let's look at the right triangle that includes vertex E and apply the Pythagorean theorem. This is the hypotenuse. Its length is 1 plus y squared over 2. So that quantity squared equals h squared plus this length, which is z over 2 plus y quantity squared. I've also got a right triangle whose third vertex is V, and for that one the hypotenuse is 1. It again has a side of length h, and the other side has length z over 2. I'll subtract the bottom equation from the top equation. So I have 1 plus y squared over 2 squared, and subtract 1 from it. I have h squared in both equations, so that cancels out. So what I have to do is multiply out y plus z over 2 squared, and then subtract from it z over 2 squared. And I don't have very much left. The 1's cancel out. Y squared cancels out. I find that y to the 4th over 4 is equal to y times z, or z equals y cubed over 4. And for any value of y that I choose, which in turn determines the position of E, z will have the value y cubed over 4. Now I've just got to reverse that construction. So now what have I got? I start with z, and I construct an isosceles triangle whose base is z and whose other two sides are both equal to 1. That's straightforward Euclidean construction. I extend the base of the triangle BC to the right. Only I don't know where point E is. I extend AC an equal distance further along to D, and then I construct a line that goes through D and B. So I now have everything except this blue line. If I can draw this blue line so that this length is 1, I will have replicated my previous diagram. And I can do that with the aid of my marked ruler. So I take the marked ruler and place it so that one mark is at E, the other mark is at F, and the marked ruler itself passes through point A. At that point, I have reconstructed my original diagram, and I know the relation between y and z. Z, you'll recall, was made equal to y cubed over 4. So when I have succeeded in replicating that diagram, I still have the same relationship between y and z. In other words, y is equal to the cube root of 4z. Now this is very nice because it turns out that you can solve an arbitrary cubic equation if you can do two things. If you can trisect an arbitrary angle, and if you can take the cube root of an arbitrary real number. There are two cases that arise when you're solving a cubic equation. One case leads to the angle trisection problem. The other case leads to the cube root problem. It depends on whether the quadratic equation has 3 real roots or has 1 real root and a pair of complex roots. So we now have a set of constructions that will let us solve any cubic equation. And the only cheat is 2 marks on the straightedge.